Okay, in today's lesson we'll be looking at reactions and equations with our key learning objectives to be able to identify types of bonding in compounds, represent compounds using formulas, so just instead of using just word equations, be able to actually write formulas for these compounds, and the final one to explain and show conservation of mass in chemical equations. And this last one is actually a higher tier question or learning objective and will only come up in the higher tier papers. So if we look at the first slide, we've got two elements here. We've got lithium and fluorine, and we'll look at how these bond. Okay, and I think a key thing we need to look at is that actually this is bonding between metals and non-metals. So the metals come up on the left side of the periodic table, and the non-metals come up on the right side. So lithium is an example of a metal. It is in group 1, and we've got fluorine, which is an example of a non-metal, which comes up in group 7. So if we have a quick look at the structure of these, so the atomic structure or the electronic structure, that's there for lithium, and a similar thing, oops, and a similar thing for fluorine. Okay, so first thing you'll notice is actually the electrons are represented differently on both atoms. And this isn't saying that the electrons are different, they're actually exactly the same, but it just shows you that the dots are for the lithium and the crosses are for the fluorine electrons. Just to state again, the electrons are exactly the same, it's just showing you where the electrons are coming from. And this will make more sense in a little bit. So I'm just going to turn this around so it's a little bit easier later on. Okay. One important thing for you to know is that atoms, their key goal, the thing they want to do is to achieve a full outer shell of electrons. And they can do this in two ways. They can either lose electrons or gain electrons. If they lose electrons, they will move into their inner shell or move into a shell, the next shell down. So for example, lithium, if it lost that electron, it would move down to its first shell and therefore have a full outer shell because it's moved into the shell underneath, which is full with 2 electrons. Same thing with fluorine. If it lost all of its 7 electrons from the outside, it would move down into its next shell, and the actual outer shell then is full. The opposite is they can gain electrons, so lithium could gain 7 electrons and fill its outer shell and have a full outer shell that way, and fluorine as well could gain 1 electron and fill its outer shell. Now, the atoms actually do it the easiest way, so whichever's easier. So it's as easy to lose electron as it is to gain an electron. So we're going to say for lithium we could do one of two things. We could either gain 7 electrons or we could lose 1 electron for the outer shell. And it is easier to lose 1 electron. With fluorine, you can either it can gain 1 electron or lose 7 electrons. So it's going to do the easiest one, and the easiest ones are for this one, the lithium to lose 1 electron, and for the fluorine to gain 1 electron to fill that outer shell. Okay, so lithium's going to lose its an electron, so it's going to lose here. That one's going to go. And then it moves down to the shell. And as you can see, now that is a full outer shell. However, it is no longer an atom. To be an atom, it has to have the same number of protons as electrons. It doesn't have that anymore. So, in its nucleus, if you look at the numbers for lithium, it has 3 protons. Electrons, it used to have 3. So protons are positive, electrons are negative. So when you actually add that charge up, there was 0 charge on the atom. And to be an atom, it has to have that. But now, it's no longer got 3 electrons. It's got 2 electrons. So the charge is actually 3 positive, 2 negative, so you've got a 1 positive charge. And the way we show that is by doing this. Put some brackets around it, and we put the charge in the top right corner. If it's only a single positive charge, you only have to write positive, a single positive. You don't have to write +1. Okay, so we don't have to write that. It's no longer an ion. It's no longer an atom either at the moment. It is now an ion. Like this, call it an ion. All that means is it's an atom with a charge on it. So this is now the lithium ion. Okay. Now, a similar thing happens with fluorine. It needs to gain an electron. It's going to gain that electron from the one that lithium's lost. So it gains that electron, it goes there. As you can see, that is now, the fluorine has got a full outer shell of electrons. Okay. However, it is no longer an atom for the same reason before, because it's charged, and I can show you it's charged by doing this. Okay, so the number of protons in fluorine is 9. So we've got protons is 9, and each one holds a positive charge, so you've got a positive 9. Electrons, remember, in an atom, you have exactly the same number. So originally, it had 9 electrons, and that produces a 0 charge. However, now you have gained an extra electron. So you've actually got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So you've got 10 negative charges, and that gives you an overall charge of -1. Same way as we represented the lithium ion, we represent the fluorine as an ion. Okay, so the brackets and the negative charge there. Okay, however, it's slightly different. With a negative ion, we change the wording. So this is a fluoride ion. Okay, so you add the IDE to the end. So that shows you how the atoms become ions for this need to fill their outer shells. Now they formed ions. Okay, so they're charged. And what's going to happen now is they're going to form what's called an ionic bond. Okay? And this is how lithium and fluorine bond, and it's actually written like this. Okay? And the reason they bond is there's an attraction between the positive charge and the negative charge. And this attraction causes them to bond. Okay? And also, the attraction cancels out the charges. So one positive charge is cancelled out, but the one negative charge, and they bond together to form lithium fluoride. And the reason lithium fluoride is only Li1, F1, but remember we don't actually write those ones, is because of this reason. There's only one positive charge and one negative charge, and therefore one lithium will balance out one fluorine. Well, one lithium ion will balance one fluoride ion out, and that will become lithium fluoride. Okay, so again, you've got a metal and a non-metal. This time you've got magnesium, which is in group 2, and chlorine, which is a group 7 element. So from the fact magnesium is in group 2, you should be able to know straight away magnesium has got 2 electrons in its outer shell, which is there. Okay, and because chlorine's in group 7, straight away you should know chlorine has got 7 electrons in its outer shell. Magnesium's got 2 electrons in its outer shell. It wants to lose those 2 electrons. So what's going to happen is I'm just going to move them here to show that they've been lost. Okay, so that's 1 electron, that's 2 electrons, and we'll just get rid of that shell. Remember, that black line is called a shell, but there's not actually anything there. Just like the moon orbits the Earth, and we'd represent that as a circle going around the Earth, that isn't actually there. It's just showing the pathway or the possible places the electrons could be. Now, it's the magnesium ion now, so it's no longer a magnesium atom, it's become an ion, and the reason it's an ion is now it's charged. So if you look, magnesium has got 12 protons, which means it's got 12 positive charges. However, and it had 12 electrons originally, but now, because it's lost 2, it's only got 10 electrons. So, 10 electrons, each one giving a negative charge, means you've got 10 negative charges. You cancel the ones out, and you're left with 2 positive charge. Let me show you that. Put in 2 positive. Now you do have to put the number because you're showing the charge. So that's 2 positive. Now chlorine needs 1 electron. Okay, so it's going to take one of magnesium's electrons and fill its outer shell. But it's now the chloride ion. Remember, you had the IDE. And it's also charged. It's got 1 negative charge. But we've still got this 1 electron. We need to get rid of that because magnesium can't just throw it away. It has to be taken by something. The chlorine is taking that electron. Okay, so what we have to do is get another chlorine. And this happens again. So if you imagine this one happens twice. Okay, so you've got another chlorine ion. I'm just going to draw it. Oops. The outside shell. So it's got 1, 2, 3, 4, 5, 6, 7 electrons. That other chlorine is going to gain this electron. So now all the electrons are in place. The charges are also balanced. You've got a 2+ from 1 magnesium and a minus from 2 chloride ions. So you've got 2 minuses and 2 positives. The way you'd write this is MgCl2. Okay, so you've got 1 magnesium with a 2 positive charge, and to counter that 2 positive charge, you have to have 2 chloride ions, each with 1 negative charge. Okay, so that's ionic bonding, and that happens between metals and non-metals. The key thing you need to know that ionic bonding is the transfer of electrons. Okay, it happens between metals and non-metals. So metals become positive ions by losing or by loss, and non-metals become negative ions by gaining electrons. And that's it. If you're able to understand why that is, that's even better. And also it says you don't even need to know anything above the transfer of 1 electron. So this between magnesium and chlorine is the transfer of 2 electrons, and you wouldn't be required to know that at C1 level. Okay, so now we're going to look at between non-metals and metals. Chlorine is a non-metal, it's in group 7, and hydrogen is a non-metal also, it's in group 1. If you look at chlorine, it needs 1 electron to fill its outer shell, and so does hydrogen. Because remember, that first shell only requires 2 electrons. So you could transfer the electrons, but actually between non-metals and non-metals, there's actually something called covalent bonding. So it's not ionic bonding, it's not the transfer of electrons, it's covalent bonding. And what actually happens is, it shares the electrons. What we should really do is actually represent that electron differently. It should be represented as a circle, so we'll put it as a green circle to make it a bit more clear. Okay, so it should be represented as a green circle. So that electron we know is coming from the hydrogen, and the crosses from the lithium, but they're sharing the electrons. You've got a pair of shared electrons, and that's called a covalent bond. Okay, and if you look, hydrogen has now got two electrons. It's our shell. It's at the first shell, so two's full. And lithium, so I don't want to put lithium, chlorine has got 1, 2, 3, 4, 5, 6, 7, 8. So both of them are full outer shells. So they've gained what they wanted to. They're not charged either, okay? So it's the sharing of electrons. And we call this a molecule. If it's covalently bonded, it is called a molecule. If it's ionically bonded, it's called an ionic compound. They're different. You can't use molecule as a cover-all term, like we've done in Key Stage 3. A molecule is a covalently bonded compound, and it happens between non-metals and non-metals. So you've got hydrogen and oxygen. So have a go at this on your own and think about what's going to happen. Maybe pause it and have a think. Okay, so what's going to happen is you've got the hydrogen and the oxygen. Oxygen requires two electrons. Okay, hydrogen has only got one to share, and it only wants one as well, so it's not going to bond twice with oxygen. So what needs to happen is, if you look, covalent bond would form here. Okay, hydrogen's now happy. It's got two electrons in its outer shell. It's sharing the two electrons. It's full. Oxygen, however, has only got 7 electrons in its outer shell now. Okay, so what it needs to happen is we need to have another hydrogen involved. Okay, so that other hydrogen will bond with the oxygen. Oxygen's now full outer shell. This hydrogen's got a full outer shell. This hydrogen's got a full outer shell. And this is actually water. This is why you should be able to now tell me why water is referred to as H2O. It's got 2 hydrogen atoms and 1 oxygen atom. And the reason it's got 2 hydrogen atoms is because it needs 2 electrons to fill the oxygen's outer shell. This is what AQA give you. It is in the front of your booklet, and it states when an element reacts to atoms joining with other atoms to form compounds, this involves giving, taking, or sharing electrons. So the giving and taking is talking about ionic bonding, and the sharing of electrons is talking about covalent bonding. Ions, again, is linked to this, so the giving and taking, and molecules is linked to the covalent bonding, which is the sharing of electrons. Compounds formed from metals and non-metals consist of ions. Compounds formed from non-metals consist of molecules. In molecules, the atoms are held together by covalent bonds. Okay, so now we're going to look at chemical equations. We've got 2 types of chemical equations here. They're the same equation. We've got a word equation, which is here, and you've got a symbol equation below. Now, the word equation doesn't tell us very much. It tells us our reactants, which are the things we start with, the things that we're going to react, and they tell us our products, the things we're going to produce. And that's it, really. It doesn't tell us more than that. It's quite a simple thing. We use it more in Key Stage 3. And as we move into Key Stage 4 and Key Stage 5, we start using the symbol equations a lot more. Now, the symbol equations tells us a lot more things. So to start with, it still tells us our reactants and products. It tells us we've got magnesium and hydrochloric acid reacting to produce magnesium chloride and hydrogen. The additional things it tells us are the state symbols of each substance. So it tells us that magnesium is a solid and hydrogen is a gas. Okay, so it tells us the state symbols. Also, it tells us the number of atoms in each compound. Okay, so this little number near the chlorine we call a subscript, and it tells us that we've got magnesium, because there's no number there, so really this should be a 1, but we don't draw the 1. So it's got 1 magnesium and it's got 2 chlorines. Okay, so the subscript is specific to the atom it's after. Okay, so the chlorine has 2 chlorines. It doesn't affect the magnesium at all. Okay, it's specific to the chlorine and only the atom that it's after. And one thing you should see is actually this is an unbalanced symbol equation. So if you take, for example, we've got one hydrogen on this side, we've actually got two hydrogens on this side. We cannot produce any more atoms than what we start with. It's not possible. Okay, alchemists in the Middle Ages tried to do it with gold. They tried to produce gold as an element. They tried to change other elements into gold. It's not possible. You cannot produce an element from another element. It's impossible. And the same with this. You can't produce more of an element or more atoms of an element if you haven't started with that. It might be in a compound and you can break it away from that compound and you actually end up with more, but you can't change the number of atoms. So if you start with one hydrogen atom, you can only produce one hydrogen atom. Well, in this case, if you're producing two hydrogen atoms, you had to start with two. And the reason this isn't showing this at the moment is because it's unbalanced. So we're going to try and balance it now. We're going to go through a few rules. Okay, the first rule is you have to write down all elements. Okay, it doesn't matter if they're in a compound, you write them down separately. So I don't want to see this, HCl. That's not an element. Okay, I want to see them written down as their elements. So you've got magnesium, you've got a magnesium atom, you've got a hydrogen atom, and you've got a chlorine atom. Okay, so you write them down individually, even though some of them are in compounds. Now, I've only looked at the left side, but it is chemically and physically impossible, like I said before, to produce anything that we don't start with. So I know I've only got magnesium, hydrogen, and chlorine on the left side, so I'm only going to have magnesium, hydrogen, chlorine on the right side. If that's not the case, then the equation is wrong. However, the numbers are wrong because it's not balanced. So the second thing we need to do is write down the numbers of each atom. So how many there are. Okay, so for example, magnesium, we've got one magnesium on the reactant side. So we've got a 1 there. We've only got one magnesium on the product side. And there. We've got one hydrogen on the reactant side, but we've got two hydrogens. Remember that coefficient tells you you've got two hydrogens on the product side. Chlorine, we've got one chlorine on the reactant side. We've got two. So you should see now that this is not a balanced equation. We're actually saying we're going to produce more hydrogen. Okay, more hydrogen atoms than what we started with. We actually do produce more hydrogen because the hydrogen is locked into the hydrogen chloride. But we're saying at the moment we're producing more hydrogen atoms. And that's not true. Okay, so we've got to balance this equation. So the third step is to identify the most unbalanced. The most unbalanced element and balance it. Okay. In this equation, the two unbalanced ones are hydrogen and chlorine, and they're actually the same unbalance. Okay, so we need one more hydrogen and one more chlorine. So we'll take hydrogen first, and we need to actually increase on the reactant side the number of hydrogens we start with. So we've got one hydrogen, and we need to get to two. So I'm going to put 2 there. Now this number in front is actually called the coefficient. And this is different to the subscript. It actually affects the whole compound. Because what we're saying now is we've got 2 hydrogen chlorides. Okay, we've not just got one anymore. We're not saying we've got 2 hydrogens. We've got 2 hydrogen chlorides. We cannot add subscripts. We cannot change a compound. We can't say actually now hydrogen chloride is H2Cl. That is impossible. Okay, we can't change that. That's changing the substance. What we are doing by putting a number in front, we're changing the amount of substance. So we're going to say we're going to use 2 or double the amount of hydrochloric acid. By doing that, we increase the number of hydrogen atoms there are in there. So that's 2. But we also increase the number of chlorines, and that's for the reason here. We've got 2 there and 2 there, because we've doubled the amount of hydrogen chloride, not just hydrogen. So we also change that to there. Okay, and now that is balanced. You've got one magnesium on the left, one magnesium on the right, 2 hydrogens on the left, 2 hydrogens on the right, 2 chlorines on the left, 2 on the right. And then, as you can see, that is a balanced equation. It's still the same equation, but we've changed the amount, so it's showing you're keeping, or you're not changing the amount of atoms you've got in there. They're exactly the same. They're just being bonded differently. So we're going to go to another example. Okay, we've got methane and oxygen. So you've got the word equation there, and you've also got the symbol equation underneath. So again, the first step, you might want to pause this now and have a go for yourself, see if you can do it. But the elements we've got carbon, hydrogen, and oxygen. On the left, we've got 1 carbon, 4 hydrogens, 2 oxygens. And on the right, we've got 1 carbon. We've actually got, and this is where a lot of people go wrong, we've got 2 oxygens in there. Also, water's given us 1 oxygen as well, so we've got a total of 3. 3 oxygens. And we've got 2 hydrogens. Okay, as you can see, these aren't balanced. You've not got hydrogen balance or oxygen balance. Remember, the rule is we look for the most unbalanced. The most unbalanced at the moment is the hydrogen. Okay, because we've got 2 less. So we're going to try and increase the hydrogen to start with. We need to go from 2 hydrogens to 4. So we're going to double this. That gives us 2. Remember, that tells us now, it's not saying it's 2 hydrogens, it's saying it's 2 waters. Okay, and that gives us 4 hydrogens now. And we change that on our equation, so we get that to 4. Oops, open that one again. Get rid of that. That changes that to 4. And it changes the oxygen as well. Okay, so we started off with 3 oxygens. We've now got 1, 2, and 2 here, so that's 4. So we've got 4 oxygens. And that's unbalanced. That's still made the oxygen unbalanced, but it's even made it more unbalanced now. But the hydrogen and carbon are balanced. So what we need to look at now is looking at the left side, the reactant side. As you can see, we've got no oxygen in there, so there's no point in changing that one. We've got oxygen here. And we need to make 4 oxygens. Oxygen is in diatomic, so it's got 2. So if we put 2 there, that's 2 times 2, so that's saying we've got 2 O2s. And that gives us 4 oxygens. And that's now balanced. Okay? We're conserving the number of atoms. We're not changing that. We've got one more example. This is the respiration equation. So you've got glucose reacting with oxygen, which is carbon dioxide and water. And this is actually quite a difficult equation. And if you're able to do this, you'll be able to do any that they give you. So we're going to follow the same rules. Look what elements we've got. We've got carbon, we've got hydrogen, we've got oxygen. How many have we got? We've got 6 carbons on the left, we've got 12 hydrogens on the left, and we've got 6 plus 2 oxygens. So we've got 8 oxygens on the left side. Okay, again, we've got 1 carbon this side, 2 plus a third, 3 oxygens, and 2 hydrogens. As you can see, this is quite unbalanced. So we're going to start off with hydrogen. We could either start off with carbon or hydrogen. They're both in the ratios the same unbalance, so it's a 6:1 ratio for carbon and a 12:2 or a 6:1 for hydrogen. I'm going to start off with hydrogen because that looks like the most unbalanced at the moment. Okay, hydrogen is only 1 compound, and this is another reason we should look at what's in compound. So if we were to look at oxygen, oxygen is in both compounds, so it's in carbon dioxide and water. And if we're trying to balance that first, do we change the carbon dioxide or we change the water? And we're not sure. So we look at ones that have only got that are only in 1 compound. So we're going to look at hydrogen. It's only in water, so we can only change water, and we need to get 12 hydrogens. We've only got 2 at the moment. So we know we've got 2, so we've got to times that by a number to give us 12. So we times by 6. That tells us we've got 6 waters. Let's write them here. Okay, and from that you can see we've got 2, 4, 6, 8, 10, 12 hydrogens. So we've got 12 hydrogens now, so we can cancel that and write 12. However, this has changed the number of oxygens. So you can see also we've got 1, 2, 3, 4, 5, 6 oxygens, as well as the 2 over here. So that's 6 plus 2 is 8. Let's actually balance that for us. So we've got 8 oxygens. Now we need to balance the number of carbons. So we've got 6 carbons on the left. We only can change one thing on the right. That's carbon dioxide. That's the only thing that contains carbon. So we give it 6. Okay, and that gives us 6 oxygens. So it's giving us 6 CO2s. So you can see where that 6 carbons have come from. 3 there and 3 there. Again, it's changed the number of oxygens. So we've got 2, 4, 6, 8, 10, 12 oxygens on this side, as well as 6 oxygens from over here. So that's 12 plus 6 gives us 18. So that's changed the number of oxygens. It's 18 oxygens over here. We've got carbons balanced, we've got the hydrogen balance. We've got to look on the left side now to balance the oxygens. Okay, so we've got 8 oxygens at the moment. We need to get 18. We could either change the glucose compound or the oxygen compound. The glucose compound, it's got carbon and hydrogen. If we start changing that, then we've got to change all the right side again. So we don't want to do that. And we're quite lucky because we've got oxygen on its own. So we can just change that and affect that. One thing we've got to remember though, we've got 6 oxygens already in here, and we've got 1 of them. So we've got 18 oxygens to get, minus 6, because 6 of them already been given from this. We've got 12 left to get from oxygen over here. So to get 12 oxygens, we've got 6 there. 6 times 2, that's telling us we've got 6 oxygens, or 6 oxygen molecules, each with 2 in. So that tells us we've got 2, 4, 6, 8, 10, 12. We've got 12 oxygens plus 6 from over here gives us, it's wrong. Oh, plus 6 from over there, it's 18, so that's right. So that's a balance. If you were able to do that, then excellent. That's one of the hardest ones you'll be given, okay? You probably wouldn't even be given that because it's too big, okay? But you've shown that you're able to balance that equation, so well done. If you go through your booklet and answer all the other questions that you've been asked to do,